Pomeriggio riprendiamo. Grazie. Riprendiamo il nostro lavoro, diciamo, e il prossimo speaker è il professor François Loeser dell'Università di Paris-Sorbonne. Ci va a parlare dell'art of counting. Thank you very much.
Okay, so my lecture is about the art of counting. L'arte di contare. I'm very sorry not being able to speak in Italian. The theme of this series of lectures is arithmetic of number or number theory, which for me are the same. And I think everyone agrees that number theory is related with numbers. Numbers are related with counting. And so, here you see a small girl counting. So maybe these are small stones. And if I'm correct, the Latin name for these stones gave rise to the word calculus. So this is from the very beginning, calculus is associated with this idea of counting. And so what do we count? So we can count stones, we can count oranges or apples. But here we will count mathematical objects. And the idea I want to really convey in this lecture to convince you that counting is relevant not only just for the pleasure of counting, but maybe more essentially because it helps to discover new structure. And so this structure may be of different kind. In the first part, we will see some topological or geometrical structure revealed by counting. And in the second part, it will be more algebraic in nature. So in my original plan, which you can see in the abstract, I planned to have 3 parts. But when preparing the lecture, I realized that it could be too much. So I'm very sorry, but one of the parts I originally planned to explain, I will not. It's a pity because it involves mathematicians in the room. And but okay, I had to make that choice. So before starting about counting, since I want to connect this with topology or shapes, we should start by finding a way to distinguish between various shapes. So here we can see 3 kinds of shapes. So I will only talk of surfaces in this lecture. And so here there are 3 kinds of surfaces. The first one is, I don't know what these stars means, but okay. Maybe you do. Oh. And so, okay, this is a ball, and it's a spherical shape. This is supposed to be a donut, and it's in mathematics we call this a torus. They can hear me? Okay. It's better like this, I guess. Okay. I'm sorry. I just don't feel so well here, but okay. So here we see three kinds of surface shapes. So the first one is a football ball, which is supposed to be a sphere. The second one is a donut, which is what we call torus. And I'm wrong. I mean, this is a bezel. I always thought the bezel had 2 holes, but in fact, you have 3 holes. So I will say something wrong later in the talk. I'm very sorry. Yeah. So here 0 hole, and here 1 hole, and here 3 holes. And okay, so intuitively, it's clear that they are very different because of the number of holes. But how do we make a precise meaning of this notion of holes? It's not so obvious. So I will present one invariant, which is so-called Euler, which already saw Euler this morning, and Poincaré. So it's a so-called Euler-Poincaré characteristic. Sometimes it's only called Euler characteristic. And this is defined in terms of a triangulation of the surface. So here you have a triangulation of the sphere, and here a triangulation of a torus. So here you can see it's we cover the sphere with triangle-shaped pieces. They are not really triangles because they are on the sphere, so they are some kind of spherical triangles. And here we do something similar, but the triangles are smaller on the torus. So there are many ways to triangulate such objects, but we can read out some useful information from such a triangulation. So here we have a result due to Euler. So we take any triangulation of a surface, and we count the number of vertices, the number of edges, and the number of faces. Okay, so a triangle has 3 vertices, 3 edges, and 1 face. And the Euler characteristic of the surface, which I denote by chi of S, is made up with the number of vertices. You subtract the number of edges, and you add the number of faces. And the crucial result, which is due to Euler, is that this is independent of the given triangulation. Maybe it's not due to Euler, and Euler only stated it for convex surfaces, and in which case the Euler characteristic is always 1. Okay. So here is an example. You have a torus, and you have some triangulation pictured. So you have 21 vertices, 63 edges, 42 faces. And so you get chi equals 0. So you have you can take I said for the, okay, I'm sorry, I said 1, it was 2, of course. So you can take also this familiar picture from the Italian Renaissance. So you can trace this kind of objects called Masocchio in pictures by Paolo Uccello. So sometimes it's used as a capello. And if you looked very well, you will say, oh, but this is not a triangulation. The pieces are not triangles, they are rectangles. But it works, in fact, the same with rectangles, because the rectangles, they have similar properties than triangles. So triangles, you have 3 edges, 3 vertices, 3 edges, and 1 face. So 3 minus 3 plus 1 is 1. And if you take a rectangle, you have 4 vertices, 4 edges, and 1 face, so it's always also the same. So you can also count, you can take this picture and count compute the Euler characteristic from this picture too. Okay, so for the sphere you have 2, and in general if you have a surface with g holes, you get 2 minus 2g. So this way you can combinatorially define this number of holes. And I explained that for surfaces, but for higher dimensional geometric objects, you can do similarly. There is a notion of triangulations. Instead of using triangles, you use higher dimensional triangles, which are called simplices. And then you take alternating sum of a similar nature. You start by counting the number of vertices, edges, and then you have 2-dimensional faces and minus the number of 3-dimensional faces, and so on. So this is, historically, this is the start of so-called combinatorial topology, which existed before people developed the more advanced algebraic topology. Okay, so now we know what is the Euler characteristic. And now we can pass to counting. So I'm, not me, but many people are interested in counting solutions of equations. So let's start, take for a 2-variable polynomial with integer coefficient. So it's a function of 2 variables, y, x and y. And it's a polynomial in x and y with integer coefficients. So people are interested in such equations. For instance, this one was interesting for a long time to many people. You have others. And depending on, you may be interested in finding a solution with integer coefficient or with rational coefficient. It depends on the kind of problems you are interested in. Of the equation f of xy is 0. Okay, this is, of course, you can generalize to polynomials in many variables. You can take systems of equations. But for the purpose of this lecture, one equation in 2 variables is enough. Okay, imagine you are interested in solution with integer coefficients. Okay, it's very natural to start studying the congruences. So if your equation has no solution modulo 5, for instance, then there is nothing more to do. Or if it has a lot of solution modulo 5, you can hope. Sometimes it will be true, sometimes not, depends. It's a topic of research, even today. But it seems to be a good idea to study solutions modulo a prime number. Why modulo a prime number? I mean, you could look at solution modulo any natural number, but because of the Chinese remainder theorem, you get all the information you need using prime number. I'm cheating a bit. I'm cheating. I see Umberto is not so happy. But okay, so essentially, it's enough to count modulo p. Okay, it's the key point. And so we work modulo p. So this is z modulo p. So its algebraic structure is that of a field, and it's finite. In fact, it has p elements. So it makes sense to count the number of solutions of this equation viewed as an equation in this field. So originally, the equation had some integer coefficient, but you look at the classes of this coefficient modulo p, and you get element in this field fp, and you look at the solution. But you could work more naively, just saying, in terms of congruences, just I want to count the congruence classes mod p of integers x and y, satisfying f equals 0 mod p. It amounts to the same. So it's very concrete. Unfortunately, we have to introduce a somewhat more advanced technology. I mean, this field, so I denote this field by fp, which means finite with p element. And in fact, we need to consider more finite fields. And so it's a fact that for any q, which is a power of some p, there is a field fq with this number of elements. So we write it as fq. And furthermore, it's unique. What do we mean by unique? Unique means unique up to isomorphism. And in fact, this is at the same time a source of trouble and richness, because we have sometimes the whole automorphism group plays a role in the picture, and we have to use that. I mean, it's related to what Yves explained in his lecture. So a very simple example is this field. So you take a polynomial in one variable with a coefficient in the field with 3 elements, and you model it by this polynomial, x squared plus 1. I hope what I wrote is correct. It's an irreducible polynomial in this field. And so the quotient is a field, and it has 9 elements. It has 9 elements. There are many ways to check that, but it's a vector space of dimension 2 over the field F3. So a vector space of dimension n over a field with q element has q to the n elements. Just think in terms of a basis. So if it's of dimension n, it's determined by an element of this object is determined by n coefficients. And for each coefficient, you have exactly q possibilities, so you have q to the n elements. Okay, so the point is that all finite fields can be described in this way, but unfortunately, the huge problem is there's a big difference between showing that there exists a polynomial, irreducible polynomial of the right degree, but to explicitly describe such polynomial, it's more complicated, and to explicitly compute, for instance, the table of multiplication, it's from a computability point of view, it can be difficult. But that's not a matter for us. Let's just continue by just saying that for any q, a power of a p, a prime number, there exists, so to speak, unique field with q element fq. So this is what we will consider now. And so the idea now is we fix the prime number p, and or it's not, maybe not yet fixed, but so we denote by n with pr as an index the number of solutions of f equals 0 in this field. So let's take the simplest example of a line. Okay, we have PR element, PR points in this line. I'm talking geometrically. You see, I'm an algebraic geometer. I was starting by talking about solutions of equation, and now I talk about points. This is just a professional deformation. I'm very sorry for that. But it means that I'm used to see this in geometrical terms, which of course is very useful. Sorry. So So this is a very simple example. So we have exactly PR solutions because we look at solutions that y equals 0, and so we are free to assign any value to x. I could give a slightly more complicated example by taking equations of degree 2. But already in degree 3, it's not so easy to compute. So already in degree 3, usually the computation involves so-called Gauss sums. So here's a nice picture of Gauss. And Gauss sums are, so to speak, of a transcendental nature. They are finite analogues of the classical gamma function, which is, gamma function is maybe you have seen it. It's an integral in terms of the exponential function. It's integral from 0 to plus infinity of e minus t, t to the power s minus 1 dt. And so it's highly transcendental, and these Gauss sums are transcendental. So this means that these numbers very often are complicated. You cannot compute them precisely. Of course, you can use a computer and compute them, but if you, for given p to the r, but if you want a formula in terms of p to the r, then it's very complicated and might turn out to be intractable. Okay. But here is that where the interesting features that can be explained. So we have this equation which has integral coefficient. So of course you can view it as defining a set of complex points. So we can view, you can look at the complex solution of this. So now in the two-dimensional vector space C2, which we can identify with R to the 4. So this means that this set of complex solutions is a surface, like we saw at the very beginning of my lecture. So it defines the surface. And so since it is a surface, we can consider its Euler-Poincare characteristic, which I denoted like that. And now there is a beautiful statement. Of course, disclaimer, what is written here has no meaning. And of course, the idea is to explain you what it means. No, but so I find it appealing to state the theorem like that, even if it has no meaning. So it's that you can recover the Euler characteristic of the surface of complex solutions as the limit when r goes to 0 of the number of points, number of solutions in the field with PR element. So of course so maybe I should ask, why is there no meaning to that statement? Because r is a very discrete variable. It's a positive integer, so it starts at 1 and then 2, 3. And how can you take a limit when r goes to 0? So this I will try to explain. But I think stated like that is very striking. So let's look at some examples. So of course, the trivial example of the line, the number you get, here you get p to the Okay, I'm lost because oh yes, I'm fine. Okay, so here you have p to the r, and of course it has no meaning to take the limit, but certainly the limit, I mean, it's a bit like Eve explained with Euler's computation. For Euler, if you ask Euler what is the limit of p to the r when r goes to 0, he would say it's 1. I hope so. So here you have 1. And here, what do you have? The complex solution is just the complex plane. Complex plane, it's topologically just a sphere minus 1 point. Okay, if you throw away 1 point, you get the plane. So the Euler characteristic of the sphere is 2. Okay, the Euler characteristic is additive in some sense. And so if you remove 1 point, you get 2 minus 1 is 1. Okay, so, in fact, this magical theorem is not valid for all p's. It's only valid for almost all p in the sense of for all p's except a finite number of them. And it's also valid for systems of equations in any number of variables, if you extend the definition of the Euler characteristic. Okay. And this magical statement is usually you don't find it in the literature, even in a form that makes sense, because it's a very special case of much more general results, but these much more general results are maybe more complicated to explain to a general audience. And so this is why I have chosen this form, which also I consider as quite striking. So it's a combination of results of Bernard work, so, who was an American mathematician, but who was very close to Italy. He was for several years professor in Padova. And Alexander Grothendieck. But of course, it has no sense in the way it is taught. And to give meaning to this statement, we first do as you saw in Yves' lecture. I mean, like Euler used to proceed. You have numbers, and the best way to study numbers, family of numbers, is to put them into a single series. And so here you take, so this is a bit strange, certainly strange the first time one sees it, because the natural things to do would just be to take the general series, the generating series, which should just be the sum of the np to the power r to t to the r. But here we do something a bit more involved. Okay, we divide by r, why not? I mean, divided by r is related to taking a derivative with respect to t, okay? And one applies the exponential function. So it's a bit strange, but it is like it is. Okay? And in 1960, Bernard work proved a very striking result, that this function, which people call the zeta function, but we have many things called zeta functions, but there are reasons to call this one particularly a zeta function. And he proved that this function is a rational function of the variable t. So what is a rational function? It's what you see in algebra. You have polynomials in one variable, and you have rational functions, which are just quotients of polynomials. So this apparently complicated function, as a function of t, is given by a quotient of two polynomials in t. So this is extremely strong. For instance, what does this say? I mean, so it's a series. So how do you get a series from a rational function? Just by expanding the denominator into series. So for instance, if you have denominator is, say, 1 plus t, you know the development as a series of 1 over 1 plus t. And in general, you just decompose. These are complex polynomials. You just decompose the denominator into linear factors, and you consider the corresponding series. So it already shows, you already get something very non-trivial. So if you, of course, a rational function, but it has a finite number of coefficients. It's a question of polynomial. So you have a finite number of coefficients. So if you develop it as a series, you get an infinite number of coefficients. But you get immediately that, in fact, this infinite number of coefficients, they depend only of a finite number of them. So it says that if it's enough to know a finite number of these guys, to know all of them. This is very striking. And in fact, if you have bounds on the degrees, you know how many of these numbers you need to. This is extremely useful for computation, for instance. And in fact, you have characterization of power series which arise from rational functions. In fact, without this exponential series, there is a very simple criterion which I did not write on the, but essentially the coefficient of a rational power series satisfy linear recurrences. And it's a characterization. But here, because you have taken the exponential and so on, you get some other kind of characterization. You get that there are some a finite family of complex numbers which depend on P, and your number can be, NPR can be written as the sum of the alphas to the power r minus the sum of the betas to the power r. In fact, the alphas and the betas they are essentially the roots of the polynomials occurring at the numerator and the denominator. And now, so you see, we have made a lot of, we know much more about how this number NPR depends on R as a variable. Before, we knew only that it was defined for positive integers, but here we have some reasonably nice functions of R. They may not converge everywhere on the complex plane, for instance, but you can do something. It's an exponential polynomial, and so one can interpolate it by some continuous function. In fact, the way to proceed, since I will take advantage of, once again, of Yves' lecture, Yves mentioned that you can do, of course, analysis about the reals of the complex number, but you can also use periodic numbers. So here, I will not talk about periodic number because P is already, there's already one prime P. So let's take another prime number. We usually call it L. I mean, there is a classical joke about the Orsenman department that they are not aware of that there is an infinite number of primes because they only know 2 P and L. So let's call the other prime number L. And so doing some L-adic analysis, just meaning that you've used this function of R as function on this, as some open on this space ZL, you can interpolate it, these values by the values of a continuous function, which allows to give a meaning to the limit at R. That's right. So let's say it again. So knowing that the function is rational tells us a lot about the structure of this number, and it tells us enough to give a meaning to the limit. So this explains the first part of the statement that these numbers have a limit. And now there is a second part of the statement that is related to the other characteristic. And here, on the right-hand side, of course, the limit, it's because we take the alphas and betas not 0. The limit is in fact the number of alphas minus the number of betas. So in terms of the polynomials occurring on the denominator and numerator of the zeta function. This is, in fact, the degree of maybe the denominator minus the degree of the numerator. So it's essentially up to sign, it's the degree of the rational function. And then there is this Grothendieck part. It follows from much more precise and general statement by Grothendieck that, in fact, the degree of the zeta function is related to the Euler characteristic, and this explains this marvelous statement. So, in fact, the connection between number of solutions of equation in finite field and the topology of the set of complex solutions, which is an example of, this was already in the vision by André Weil in a very influential paper at the end of the 40s. So here I want to show you some excerpts of this paper. So you see, okay, let's take a variety, just a set defined by a polynomial equation. So there is some, it should be non-singular, okay? And he considered this function zeta, but if you think about it, it's just the same with the one we saw, because you take the log of it, which removes the exponential, and then it takes the derivative, which provides for the denominator. So this is exactly the definition of the zeta function. And so, okay, this is just fantasy. At the time it was not proven, it's a series of conjectures. And so in his vision, this zeta function should satisfy a functional equation. And in the functional equation, you have the chi here, where the chi is the holocompare characteristic, which we saw. Okay? And he also predicts the rationality. And he says much more, because so this is where the non-singularity condition plays a role. In this case, not in the general case, you have these alphas as a very specific complex absolute value in terms of Q. And these polynomials, they are related to the so-called Betti numbers. So I did not want to define the Betti numbers, but Betti numbers is something more refined than Euler characteristic. So Euler characteristic is a kind of global invariant, and the Betti numbers, they, so to speak, describe the topology in each dimension. And the connection is that the Euler characteristic is the alternative sum of the Betti numbers. And here it's a key. The evidence at hand seems to suggest that if you have a variety without singular point over a field of valueless numbers, say Q, the Betti numbers of the varieties derived by reduction modulo P or Q are equal to the Betti numbers of the variety over the complex number in the sense of combinatorial topology for almost all P's. So what I explained to you is a very special case of things which were envisioned by André Weil at the end of the 40s. And of course, to achieve this program, it took many years. So surprisingly, because this was not the way it was supposed to be, Dwork was able to prove rationality first, and then the Grothendieck machinery provided functional equation and another proof of rationality, and also comparison with the complex points. And the more difficult part was this statement about absolute values, which is in some sense an analog of the Riemann hypothesis, and this was proved in the 70s by Delin, and he was awarded both the Fields Medal and the Nobel Prize for it. Okay, so this is for this connection. So here I want to mention two connections. A fruitful interplay between combinatorics and geometry. So here you see Michel de Mazur, who fortunately still very young, and he introduced he's an algebraic geometer, and he introduced algebraic objects from algebraic geometry called varieties, which are defined into purely combinatorial terms. And there is a funny story, I hope so, he told me, is that he introduced that because he believed that combinatorics would help to prove new theorems in algebraic geometry. And then he realized that combinatorics, even of polyhedra, which you think you understand what polyhedra are, but in fact you don't, because in high dimensions the polyhedra are something very complicated. And he realized that in fact it was too hard to use the combinatorics of polyhedra to use this dictionary he introduced. But other people, they worked the other way, and this was very fruitful until now. So they use advanced algebraic geometry to prove statement on combinatorics. So here you see, like before, counting point is tight, but you cannot do it so much. And you need to know about structure to go beyond that. Here, it's geometry that may help to prove statement in combinatorics, while you would think that it's more easier the other way. But in fact, de Mazur told me he did not expect it would go the other way, and he was surprised at that. And also, just to say a few words about what Go did, which also awarded him the Fields Medal. So he proved something called the fundamental lemma. You can reduce it to an equality between the number of points in finite fields of two different systems of equations. So you have two different systems of equations, which are very special nature, and you look at these numbers n, p, r on both sides, and they are equal. But you cannot prove it because you cannot compute them. The easiest way to prove that two numbers are equal is to compute them, but it does not explain why they're equal. Okay? And here to introduce a very sophisticated geometry to prove just the equality between those numbers. So in fact, the fact that number of points are related to geometry is extremely useful to prove properties of this number. So it's not because it looks more elementary that it does not involve rich geometry behind. Okay, so this was just some kind of short interview. And now I start with the second part of the talk, which is, it's supposed to be much shorter, so you should not worry. Okay, so now, so this is, I hope this is supposed to be very elementary. I take 2 points in the plane, which are supposed to be distant, and everyone knows that there is a unique line passing through these 2 points. Oh, maybe I should be here. There is a unique line passing through the 2 points. Okay, that's nice. We know that, but yes, we know that, but what? Okay, now we take 5 points in the point. Okay, here this is okay, except if the 2 points are equal. So everyone will agree that if they're equal, they cannot be called being in general position. General position means avoiding certain special configurations. Here we take 5 points in general position, and there is exactly one conic passing through it. So let me show you. Here you have 1 point, 2 points, 3 points, 4 points. So you have these 4 points. And if you vary the 5th points, you get different conics. So if, for instance, you take as a 5th point this one, you get this red conic. And yeah, and if you take this one, you have this conic, so, and if you take this point, you have this conic. I mean, it's a slightly disturbing because, so here you have 4 conics, but some are connected, like the red ones are ellipses, and the other one, they are hyperbolas, I guess. Okay. So this is the classical theorem, and here you have a similar picture. That's nice. Okay. Now we take 8 points in general position, and exactly 12 cubic, so this means curve of degree 3. Rational. So what do I mean by rational? Rational means with a rational parameterization. So it's like we do at school. I mean, you can describe plane curves by parameterization. So x of t, y of t, and you ask that as a function of t, x and y are rational functions of t. So for instance, you know that the circle has a certain rational parameterization. It's 2t over 1 plus t squared, 1 minus t squared over 1 plus t squared. Okay? So, and in degree t, everyone has a rational parameterization, but if you, from degree 3 on, it's an additional condition. Okay, so that's nice. And then it goes on. You take 11 points in general position, and you have exactly, okay, 612 T rational quartics. This is due, if I'm not wrong, to Zeuthen in something like in the end of the 19th century. And okay, so that's nice, but this looks like some kind of, it's nice, but it looks very kind of anecdote and maybe a zoology of mathematics. We all like this kind of mathematics, but okay, for fun it's nice, but okay, there are more numbers. So here you have the degrees of the rational curve, so the line, the conic, the rational cubic, and so on. Here you have the number of points in general position, so it's always 3D minus 1, so it's, in fact, it starts with 2, then 5, 8. And then you have the numbers of this curve, rational curve of degree d passing through this point, so these are the numbers we described. In fact, if I'm not wrong, starting from degree 6, these numbers were not known before, I mean, 30 years ago, they were not known. It's not that they were not known. I think people were not even guessing that it would be possible to compute them and that it would be interesting. Okay, so these are the numbers. So now I can ask you a question. Can you, from this, you have 12 numbers. So if you have a sequence of 12 numbers, you should be able to guess the pattern. So can you tell me the general rule behind? Of course not. Of course not, but there is a general formula due to Kontsevich. So I hope you can see it. So it's, you have these NDs and you have an equality here. So you want to compute the ND. So you have two sides. On the left-hand side, you have ND, and you have this ugly sum, but which is not that ugly because here you have binomial coefficients. And in fact, you have D, and you cut D in a sum of two guys, all of them both non-zero. So this is, and one is called DA, the other one DB. And so here you have the degrees, DA, DB, and DB. And the other numbers in the picture are just the n corresponding to these DAs and DBs. So by induction, they are supposed to be known. And on the right-hand side, you have a similar expression but no ND. So this means that there is an explicit formula to compute ND by induction. So now you can tell me, very nice, we have this formula but okay, this formula does not seem so, it's a bit strange and it does not seem to reflect any structural fact, or we don't know why this formula is true. And in fact, there is a structure behind the formula. The formula expresses the associativity of a certain algebraic structure. And so I think this is what I really want to convince you of. So we had certain crazy numbers that we did not even care to compute. And mathematicians even did not imagine that one could compute them. Then you get a formula which in fact came from physics to compute them. And the formula itself is not so nice at first sight and looks a bit weird. And at the end of the game, you can explain everything in a conceptual way by introducing an algebraic structure, which of course I won't describe, but it has a nice name, quantum cohomology of the plane. I mean, looks like some kind of James Bond movie. And there is a product on this, and it's associative, so you have a convincing explanation of why these numbers are computable and why they satisfy this quite weird, this quite weird formula. So I think it's the end of my talk.